For number 2, the number of bacteria in a culture is increasing according to the law of exponential growth. That's important, law of exponential growth. So we are going to be using y equals a e to the RT. Okay, R is positive because it's growing. After 1 hour, there are 100 bacteria, and after 2 hours, there are 200 bacteria. We want to know how much bacteria there will be after 3 hours. Well, unfortunately, we don't know how much bacteria we started with, and we don't know our rate. So we need to find out both of those things. So first, I'm going to use this information. After 1 hour, there's 100. Okay, so I'm going to plug that in. So my y is 100 a e to the r times 1. And I also know that after 2 hours, there's 200. So I also know that 200 equals a e to the r times 2. Okay, so I've got 2 different equations and 2 unknowns, so I can solve this. So in this first equation, I am going to solve for a. Okay, so to solve for a, I'm just going to divide both sides by e to the r. Okay, so that'll make these cancel out, so I get a equals 100 over e to the r. Now, I'm going to take that and plug it into this equation. So I get 200 equals, instead of a, I'm plugging in 100 e to the r times e to the 2r. Okay, so we get 200 equals 100. Now, with I have e to the 2r on top and e to the r on bottom, so remember you can subtract your exponents when one's on top, one's on the bottom. So that's just going to give me e to the r. Okay, so now I can divide both sides by 100. I get 2 equals e to the r. I need to find out what r is, so I'm going to take the natural log of both sides, which will bring the r down in front, and the natural log of e is just 1, so that's gone. So I end up with r equals the natural log of 2. And if we use our calculator on that, we end up with 0.693. Now, I realize I'm going to have a little bit of a rounding error by doing it this way, but that's okay. I'm willing to deal with that. Okay, now let's come back over here. Let's take that over here. Coming back to this equation, we know that a equals 100 divided by e to the r, and now we know what r is, 0.693. So we plug that all into our calculator, 100 divided by e to the 0.693, and we end up with a is approximately 50. So now we know our initial amount of bacteria and we know what our rate is. Those are 2 really important things, our initial amount of bacteria and our rate. Okay, so now let's get to solving the problem. We want to know how many bacteria is there after 3 hours. So go back to that original equation. We're trying to find the amount after 3 hours. We said A was 50, that's what we started with. E, our rate is 0.693, and now our time is 3 hours. Now all we have to do is plug that into our calculator, 50 times e to the 0.693 times 3, and when we punch those buttons, we get right around 400 bacteria. Final answer. All right, number 3 is a very similar problem. A fossil originally contained 6.5 grams of carbon-14, which has a half-life of 5,715 years. How much carbon-14 will remain after 1,000 years? There's actually 2 problems here, okay, so we're going to stop there. So let's see. We're talking about carbon decay, so the formula that we're going to be working with is A e to the negative RT, okay, because carbon is decaying. Okay, we know how much we initially have. This is our A, but we don't know our rate. Until we can figure out our rate, we're not going to be able to plug in. So we have to pause a little bit and think about our rate. We do know that it has a half-life. Okay, so whatever amount you started with, let's say I started with 1 gram. Whatever amount I started with, whatever its rate was after 5,715 years, I'm going to have half of this, so 0.5. Okay, and I'm going to use this information to find out what R is. Okay, So this is just 1e, we can ignore the 1. We need to take the natural log of both sides so that we can bring this down in front. That got a little messy, but we have the natural log of 0.5 equals negative 5715r, and this is the natural log of e, which we can cancel out. So now we can solve for r, just divide both sides by negative 5715. And we end up with r as 0.00012. Okay, now we have enough information to answer the question they originally asked. So go back to this formula. Oh, how about a, e? Oh dear, let's try that again. Y equals a e to the rt. So we want to know how much will remain after 1,000 years. Okay, so we started with 6.5 grams. Our rate is negative 0.00012, and we have 1,000 years. So we plug that into our calculator, 6.5 times e to the negative 0.00012 times 1,000, and we end up with 5.76 grams. Okay. So that answers the first question they asked us. So now, suppose we have a 1,000-year-old fossil and there's 2 grams of carbon-14. We want to know what's the initial quality. So now we have time and we know what y is. We are looking for the initial, so we're looking for a this time. So if we go back to this equation, the fossil we found has 2 grams of carbon. We don't know what it started out with. Our rate's still the same, that doesn't change, 0.00012, and we're multiplying that times 1,000. I apologize for running out of room there. So we need to solve for a, which means we need to divide both sides by e to the negative 0.00012 times 1,000. So a is going to be 2 divided by e to the negative 0.00012 times 1,000. And once you do all that lovely math in your calculator, you find that it's approximately 2.25 grams. Now, I definitely encourage you, as we're going through these problems, if you need to pause, because I know I'm going a little bit faster with the calculations, if you need to pause so you have time to put it in your calculator, please do that. Make sure that you're getting the right things to happen on your calculator, putting the parentheses in the right places and all of that. We'll do the back side of the paper in the next video.